All right, so welcome everybody. This is the FLOW seminar, where FLOW stands for Federated Learning One Word Seminar. And this is a seminar organized by Peter Richtarik, myself, Virginia Smith, Aurélien Ballet, Dana Ristar, and Sebastian Stich. And it was created as a global online forum for the dissemination of the latest scientific research in all aspects of federated learning. Today we have, I believe, 103rd Flow Talk, and it's my great pleasure to introduce you our speaker, who is for today Jianyu Wang, who is currently a research scientist at Apple. So he received his PhD from CMU in 2022, and also his bachelor in electrical engineering from Tsinghua University in 2017. During his PhD, he was a research intern in Google Research, also in Facebook AI research. And his main research interests are in federated learning, distributed optimization, and systems for large-scale machine learning. And he won many awards, including the Qualcomm PhD Fellowship and also several Best Paper Awards, for instance, at NEVREP's 2019 Federated Learning Workshop, and also Best Poster Award at NSF Communication Efficient Distributed Optimization Workshop in 2021. And today he's going to tell us more about the unreasonable effectiveness of federated averaging with heterogeneous data. So thank you, Jianyu, to agreeing to give a talk, and looking forward to that. Please, floor is yours.
Okay, yes, thanks a lot for the introduction, Samuel. Okay, hi everyone. My name is Jianyu. It's my great pleasure to be here to present one of my recent work to you. So the title of the talk is on the unreasonable effectiveness of federated averaging with heterogeneous data. So this is a joint work we together with many great collaborators, including Rudrajit, Gauri, Satyan, Zheng, and Tong. They are from UT Austin, Carnegie Mellon University, Google Research, and HKUST. And also this is a work this is also a work done when I was a PhD student in CMU. Okay. Also, please feel free to stop me if you have any questions. I think this talk will be relatively short. So let's start with some general background and the problem formulation for federated learning to just get familiar with the notation to be used in this talk. So suppose we have a central server and a large amount of edge devices or a large amount of clients, each of which will have a local objective function FC defined on its local dataset DC. So the goal of federated learning is to minimize a global objective function FW, which is defined as a weighted average over all the local objectives. We can also write it in an expectation form just for simplicity. And the weight of each client is in proportional to the local dataset size on that client. Here C denotes the client index. So a very basic algorithmic framework to minimize this global loss objective function FW runs as follows. First, the cloud server will broadcast the global model to active clients. Then the clients will perform multiple local updates and obtain the local model changes denoted by delta IT. I is the client index and T is the index of communication runs. After that, the clients will send back these local model changes delta IT to the central server, and the central server will average all the local model changes and use the averaged value to update the global model. And all these 4 steps will repeat again and again until convergence. We note that actually in this framework, the second step, clients perform multiple local updates, actually plays a very critical role in the performance of this algorithm. And actually there can be many different ways to define how the clients perform multiple local updates. For example, the first option to perform local updates is using a very small batch size B on each client and let each client to locally run each steps of SGD. So this method is well known as federated averaging algorithm. As we shown in this paradigm, these blue arrows denote the batch computation time, and the red blocks here denotes the communication time between the clients and the server. On the other hand, we can also use a much bigger batch size, which is BH, to update the local model just once on each client. And this method is known as FedSGD in literature. So basically, this FedSGD algorithm is equivalent to mini batch SGD. So we do not need to provide a new convergence analysis for this algorithm. We can see that from this illustration, both these two options, FedSGD and Fed-averaging, they have the same computation cost and the same communication cost at each round. So initially raised question here is, which option will be better for the algorithm in terms of the convergence rate? Which one can save us more communication costs? So the answer to this question may vary in different settings, and many previous works have tried to answer this question. For example, let's first take a look for convex functions with homogeneous data across clients. So in this setting, Woodward et al. In their NeurIPS 2020 paper, they show that the optimization error upper bound for federated averaging can be decomposed into three parts. And the first part is we can consider it as some kind of bias. And the second term is an optimization error caused by stochastic gradient noise. And the third term is error caused by performing local updates. And in this error upper bound, H denotes the number of local steps, and R is a number of communication round, and the sigma denotes the scale of the stochastic gradient noise. And M here is a number of clients. So if we compare this bound with the one for Fed-SGD, which is also the one for mini-batch SGD, we can see that Fed-averaging, in the first term in the error bound in Fed-averaging is always smaller than the first term in Fed-SGD. It is smaller by H times. H is a number of local steps. And both Fed-averaging and the Fed-SGD, they have the same second term, which is caused by gradient noise. But in addition, Fed-averaging has an additional term, which is caused by performing local updates. The good news here is that this additional term actually can be very small, because it can become to or close to zero if we use a very large number of local steps H. So in that case, one can always find some parameter regimes in which Fed-averaging is probably better than Fed-SGD. And this is a pretty promising results for the federated averaging algorithm. That means we can always use Fed-averaging in the homogeneous setting to save the communication cost in distributed training. But the story will become quite different in the heterogeneous data setting. So in the heterogeneous data setting, Woodward et al. Also show that there will be another additional term in the error bound for Fed-averaging, which is an error caused by data heterogeneity. So in this additional error, theta here is a newly defined measure for the gradient dissimilarity among all the clients. We can also treat it as a measure of the data heterogeneity. So if we compare this new bound with Fed-SGD again, which does not change in the heterogeneous setting, we will see that the last term in Fed-averaging now, it will not decay to zero when we use a large number of local steps. So when we do some calculation again, we will conclude that only when the data heterogeneity zeta is very, very small, in particular smaller than 1 over the communication rounds 1 over R, we can conclude that only when this case, Fed-averaging can have a chance to outperform Fed-SGD. But otherwise, Fed-averaging will be strictly worse than Fed-SGD in terms of convergence with respect to the communication rounds. So this condition on the data heterogeneity zeta or on the gradient dissimilarity zeta is very strict in practice. So when we run Fed-averaging for many, many communication rounds, then there definitely exists a point after which this zeta will exceed the threshold 1 over R. So people summarize this convergence problem of Fed-averaging as a client drift problem. We can also intuitively understand this client drift problem using this cartoon. So suppose the global model starts the local training from the global optimum, which is highlighted by this red dot. Then the average local model changes over all the clients highlighted by these blue arrows. It may not be zero. So as a result, the global model will gradually drift away from the optimum. That means even if we start the training from the global optimum, Fed averaging will not stay at there. So this is not an expected behavior we hope the algorithm do. And a lot of previous works have dived into this problem, and they have proposed a lot of promising solutions. And this client drift problem also become a prominent research direction in the federated learning community. So how about the practical observations about the comparison between Fed averaging and the Fed SGD? People actually found that on many naturally non-ID datasets, Fed averaging can still achieve much faster convergence and better final accuracy than Fed SGD. Just like the figures I show here from Charles et al. In NeurIPS 2021, the first row corresponds to the results of Fed averaging, and the second row corresponds to the results for Fed SGD. It's clear that on multiple data sets, Fed averaging converges faster than Fed SGD. For example, on this Starkville flow dataset, after 1,500 communication runs, Fed averaging can achieve a test accuracy about 20%, and but on the other hand, Fed SGD can only achieve about 12% accuracy. So there is a big improvement in terms of the final performance of Fed averaging, and it also converges much faster. And we also have some similar observations in the original federated averaging paper from McMahon et al. In ASS 2017. So in this figure, it is clear that Fed averaging converges faster than Fed SGD. So Fed averaging corresponds to these orange lines, and Fed SGD corresponds to these blue lines. And these empirical results are quite conflict with the previous theoretical predictions. So in order to further investigate this effect of data heterogeneity, we also ran some experiments on a natural or realistic federated dataset Starkville flow. In this dataset, the data is originated from the clients or the users, so it's naturally split. So in this dataset, we compare the performance of federated averaging on both non-IID and the IID settings. The IID setting on this dataset is simulated by aggregating and shuffling all the data from clients and redistributing them back. So in these experiments, we observe that in both non-ID and IID settings, actually Fed averaging can achieve pretty similar performance. And that means data heterogeneity may have very minimal impact on federated averaging in this dataset. These experiments may also explain why some more complicated methods like scaffold or some intra-client variance reduction method cannot beat Fed averaging on this dataset. So from the above discussions, we can see that there is still a mystery around the vanilla federated averaging, which is the most basic federated learning training algorithm. While existing theory predicts vanilla Fed averaging, it's not better than Fed SGD, and many efforts are made to improve the performance of Fed averaging in the presence of data heterogeneity. Fed averaging is still very effective in practice. It can be better than Fed SGD, and it also can be better than more complex algorithms. So in this work, we aim at providing an explanation to this phenomenon and filling this gap between theory and practice. So this is a brief overview of the motivation and the background of this work. Yeah. Is there any questions so far?
So please, as a reminder, if you want to ask a question, either post it to the chat or just raise your hand and then I'll try to unmute you. So at the moment, we don't have any questions.
Okay, thanks. That's great. Okay, let's move forward. Okay, so the key contribution of this work is a proposal of the client consensus hypothesis. We can first get some intuitions for this consensus hypothesis from some cartoons. So in people's previous understandings in federated learning, there is always a client drift problem, just like we shown in this cartoon, but we conjecture that this client drift problem may only happen in some really rare worst cases. And instead, in practice, although clients can have heterogeneous data, we hypothesize that the data may have some nice properties such that the local updating directions may have some binary structure. So more specifically, if you look at the distance between the optimum highlighted by this red dot and the average local model highlighted by this green dot, maybe in the worst case, this distance will be very large. It means the client drift can be very large. But our hypothesis says that in some good settings, maybe the distance between the optimum and the average local model can be very small or even zero. And in this case, that means the global model will just stay around the optimum. That means if we start the training from the optimum, then the algorithm can just stay around as we expect. And in this case, intuitively, the data heterogeneity may have very minimal impacts on the convergence of the algorithm. So to formally describe this hypothesis, we need to first quantify the client drift. So in this work, we define the client drift in the following way. So suppose the clients start local training using deterministic gradient descent from the same point, that is the global optimum. Then the local model changes can be written as a difference between the starting point W minus the ending point WCH. C is the index of client and H is the number of local steps. And given this notation, we can also call it as a pseudo gradient. We define pseudo gradient as a normalized version of the local model changes. We normalize the local model change by the local learning rate eta and the number of local steps h. And following this, we define the average client drift at optimum as the norm of the expected pseudo gradient, expected GC. And we denote this average client drift using rho. So if we look at if we look at carefully, then we can see that actually this rho quantity it only depends on the underlying data size, and it does not depend on the actual FL training algorithm, because we can calculate the value of rho just using the deterministic gradient descent. But when we perform the FL training, we can use any other algorithms, but this value will not change. So we can treat this rho value as an intrinsic property of the underlying federated dataset. So given this definition of client drift, we are ready to state the client consensus hypothesis. The hypothesis states that on some federated learning data size, the client drift is zero or just very close to zero. That means the clients can reach kind of consensus on the optimal point. So in other words, if clients perform multiple local updates from the optimal point, maybe the local updating direction from different clients are just also gonal to each other or can be canceled out with each other. The average, so that the average local model changes is zero or almost zero. So what are the implications of this client consensus hypothesis? We conduct some convergence analysis under it and we found that it will yield a lot of promising theoretical results. For example, we can first consider a very simple case. Suppose the loss function is just strongly convex, and suppose when clients perform local updates, the local update rule is just a local deterministic gradient descent. So in this setting, we use a communication runs to achieve a target epsilon error as a metric to measure the performance of different federated learning algorithms. For FedSG, we already know from literature that the communication rate will be log 1 over epsilon, which is a linear convergence rate. Kappa here denotes the conditional number of the loss function. And if we use previous analysis technique, the vanilla federated averaging will achieve a convergence rate of 1 over epsilon square, which is significantly slower than the rate of FedSGD. So, but if we use a new analysis technique in this work, under the client consensus hypothesis, we are able to show that federated averaging still enjoys the linear convergence rate log 1 over epsilon, and it effectively reduces the condition number by h times. Recall that h is the number of local steps. So that means under client consensus hypothesis, federated averaging is strictly better than FedSGD, and it is not impacted by data heterogeneity at all. This is a very surprising result from compared to the existing analysis. So what are the differences between our new analysis and the existing analysis? Why we have so different convergence results? Let us take a closer look. So in most previous analysis, one needs to upper bound a quantity, which is a difference between the pseudo gradient GCW and the true gradient nabla FCW. So in order to upper bound this quantity, it is a common practice to use an expected norm. This is because the square of mean is always smaller than the mean of the squares. And after using this upper bound, one can further derive a uniform upper bound for the expected norm using the gradient dissimilarity assumption. This uniform bound will be some function of the gradient dissimilarity zeta. And after that, one can derive a convergence upper bound for federated averaging. But the problem here is that actually this inequality, the square of mean is always smaller than the mean of squares, may not be tight. It is very possible that when the mean is 0, the expected norm is very large. So it will lead to a pessimistic estimate of the performance of federated averaging. And instead, in our new analysis, we care more about the mean value as an optimal point. And we can show that when the client consensus hypothesis holds, the mean value as an optimal point, that is the client drift at an optimum rho, will be close to 0. And this is greatly smaller than the previous uniform bound, depending on the gradient dissimilarity zeta square. So for this reason, our new analysis can provide a more optimistic view for federated averaging. Okay. Any questions so far?
Yes, so maybe I would like to ask one question. So if I understand it correctly, then in your analysis, also like in your convergence rate, it doesn't really matter like how many local steps you run. So even like one-shot averaging would be good for your method under this assumption, right?
Yeah.
So do you maybe have like, do you think that this could be or is there actually difference whether like you run only one communication round or many for your analysis?
Yeah, I think from the analysis in this simple setting for strongly convex functions, and the local update rule is just a deterministic gradient descent, maybe just one communication round will be enough, because we can let h becomes we can set h to be a very large value, but this conclusion only apply to this simple setting. If we change the setting, for example, for convex functions, or changing the update rule to stochastic gradient descent, maybe this conclusion will not hold. We may have some additional error. Yeah.
Thank you.
Yeah. Thanks for the question. Okay, so let's move forward. So from the above discussion, we already see that using this client consensus hypothesis, we can get a very optimistic convergence rate for federated averaging. And in the following, in order to get a better understanding of this client consensus hypothesis, and also make sure this hypothesis is realistic, we construct a concrete example. And in this example, we can easily derive the closure forms of the convergence of federated averaging. And this can help us to get a better intuition. So in this concrete example, we just consider a linear regression model. So suppose that on each client C, the local data is generated from exact equation like this. So the label is an inner product of the optimal model W star and the input XCI plus some random noise epsilon CI. So the key property of this toy example is that the distribution of this epsilon CI is the same across all the clients. That means different clients share the same conditional probability. The probability of Y given X is the same across all the clients. So under this concrete example, we can easily write the closure form of the local objective function FCW like this. It is just a quadratic loss function, and the AC, BC here are just some random variables depending on the input data XCI and the epsilon CI, the noise. So we can also write the local minimum in this case as WC star, which is a summation between the optimal model W star plus some bias ACBC. So in this case, we can separately check the gradient dissimilarity and also the client drift at optimum. The good news is that we can easily derive the closure form in this simple example. So for the gradient dissimilarity, it is defined as a difference between the local gradient and the global gradient. We can show that it equals to the expected norm of the BC vector, which can be arbitrarily large and remains unbounded. So in this setting, the previous analysis, which rely on the gradient dissimilarity assumption, may just fail because they will just predict divergence of the federated averaging algorithm because we do not have a bounded gradient dissimilarity. And this will lead to a too pessimistic convergence rate for federated averaging. But on the other hand, if we check the client drift at the optimum, we can see that it will become some polynomial of the BC vector, and we take the expectation within the norm. So when we have sufficiently large number of clients, this expectation will just become to 0. So that means our client consensus hypothesis will hold in this concrete example. Under this, we can prove that we just need O1 communication in this example. Again, this conclusion only apply to this toy example where the loss function is quadratic or strongly convex, and the local updating rule is just a deterministic gradient descent. But this conclusion, we cannot arrive at this promising conclusion using the previous analysis technique, which rely on the gradient dissimilarity. Okay. We further evaluate this client consensus hypothesis, on some realistic federated data sets. That is federated EMNIS and the Sagor flow. They are both naturally non-ID at the very beginning. And we run local deterministic gradients on clients, and we also promulgate the global optimum via using pre-running centralized SGD. And we compare the average local model changes or the average model drift at the optimal point and the bound induced by gradient dissimilarity assumption, which is used in previous works. So we can first take a look at the left two plot figures. We can see that we can observe that using the gradient dissimilarity assumption, these blue lines, it always arrive at a larger bound, which is slowly increased along with the number of local steps. But in contrary, the average client drift at optimum is just close to 0. And even if we increase the number of local steps, this red curve will just remain very close to 0. And this is consistent with our client consensus hypothesis. That is, on some federated learning data sets, the average client drift at optimum is just around 0. And moreover, we also ran the same set of experiments on a pathological CFR100 dataset, where the data heterogeneity is manually constructed. So we clearly see that in this red figure, on this pathological dataset, the client consensus does not hold anymore. This red curve corresponds to the average client drift at optimum is not 0. So we conjecture that this might be the reason why some complicated methods like scaffold can beat Fed averaging on this pathological CFR100 dataset. We further check the client drift at a different time along the entire training process in the FEMNIS datasets. Again, we can see that at around 0, at around 50, and at around 100, at all times, the average model drift, as shown by this red curves, is much smaller than the bound induced by the gradient dissimilarity. And when the training comes to the end, the gap between these two curves also becomes larger. And all these experimental results validate our consensus hypothesis and show that previous theoretical analysis might be too pessimistic. Okay, now I'm going to summarize this talk. So the key insight here is that on some federated learning data sets, such as Stargo Flow, data heterogeneity may not be that scary. It may have very limited impacts on the performance of federated averaging. And we propose a client consensus hypothesis to explain this phenomenon and fill the gap between theory and practice. Moving forward, there are also a lot of future directions are ripe for explore. For example, it will be interesting to see how to identify whether a given data set has this nice property of client consensus. And also it will be interesting to define more types of data heterogeneity and study them separately. And this is a link of this work. Thanks a lot for the attention. This is all about my today's talk.
Yeah, thank you, Jianyu, for an excellent talk. And yeah, if there are any questions, please do raise your hand or just pose a question to the chat and then I can read it out loud for you. Yes, maybe let me start with a couple questions. So do you think you can actually extend this in some way to like a non-convex functions or maybe like a PL?
Yeah, I think that is one promising direction I have been tried for a while, but I would say it is a little bit difficult because the extension is not that straightforward. The reason is that in order to conduct analysis using this client consensus hypothesis, we need to use a different analysis framework other than the previous ones. So the current framework only works well with strongly convex functions. And we may need some significant revisions or modifications in order to extend it to PL function or non-convex case. Yeah, I think that would be a very interesting direction because I think personally, I really like this new analysis framework because it is much simpler. We analyze the convergence from the point of view of pseudo gradient. It can provide us a more simplified view, but the difficulty is it is difficult to extend it to general settings. Yeah. I think it will be definitely great if there are more people working on this direction. Yeah.
Thank you. Let's see whether there are questions in the chat. So maybe people are still waiting. So maybe I can ask one more. So
Sure.
again, I'm gonna like a bit follow up on the question that I asked you during the talk. So if I understood correctly, it seems that it's either like in your setup, it's either like really it's either optimal to have like a one local step or like kind of infinity. You would just do like one shot averaging, right? Do you think that actually like I don't know whether like maybe the analysis that you have in paper reveals that. Do you think that there actually might be like different number of local steps that might be optimal for a given problem? Maybe like that would require different framework or different assumptions.
Yeah, I definitely agree this. Because so just as I listed here, I definitely believe that there can be many different types of data heterogeneity. So maybe the client consensus hypothesis is just one optimal heterogeneity we capture in some data sets or in the concrete toy example. And maybe there exist some other types of data heterogeneity, just in the middle ground between the optimal and the worst case. And in that case, we may need some middle ground of the number of local steps. Yeah, and also even under client consensus hypothesis, if we let clients to perform stochastic gradient descent locally, then the number of local steps will not be will not be infinity. We will need some communication runs in order to mitigate the stochastic noise. Yeah.
Thank you.
Yeah, I'm quite excited about this direction that define more types of data heterogeneity and study them separately. Yeah, I definitely believe there should be there is a lot of space around this direction.
And do you have idea like kind of what that might be like? Can be like maybe like do the average kind of average heterogeneity in terms of like updates, right? Like instead of the optimum.
Yeah. So I think one rough idea I have is about is from the concrete toy example. So a key property in this example is that we assume clients have the same conditional probability. The property of the label given the input is the same across all the clients. And I think maybe this property can be generalized to more general cases, and maybe we can derive some positive results in general cases if we extend this property. Yeah.
Okay, so we have one question in the audience. Let me just unmute. Yeah. Okay. Yeah. Please go ahead, Jingwei.
Hi, Jianyu. Here's Jingwei from Duke. It's a great talk. Thanks for sharing. And may I ask what client selection scheme do you consider in your work?
Oh, I see. Yeah. So basically, in this paper, we just assume that all the clients will participate into training, because the focus of this paper is studying the effects of data heterogeneity. So we do not take the client selection into account. But the analysis framework we use in the paper can be extended to the client selection case. Yeah. I more rigorously, I would say that it can be extended to unbiased client selection case. Yeah.
Okay, and in your talk, you basically you are discussing the expected results of optimization, right? Expected gap between the optimal and the optimized objective, right? Have you ever consider the variance of the optimization? And
no, I haven't yet, because I'm not sure what because I saw real papers discussing the variance about the optimization error. Yeah, but that would be definitely interesting.
Yeah, that's true. And yeah, I'm just curious. Yeah, maybe from your analysis, it is convincing that in some settings, fat average can converge better than fat SGD. But when you consider the non-ID, do you really think the variance of the optimization can be, smaller for fat average? Maybe that is that's a good point to think about.
Yeah, one thing I want to clarify is that it's not accurate to say that no papers consider the variance, because if we look into the optimization error bound, people cares about the expected norm, which is the summation of the mean square and the variance. So this expected norm, it already captures the mean square and the variance, but we just didn't separately study them. And it might be straightforward to separate them, but I'm not sure about this. Yeah, but it'd be interesting to see whether fat SGD and fat averaging have different behaviors in terms of mean and variance. Yeah, it will be interesting to action.
There are several papers discussing the variance of the optimization in federated learning. I'm just curious, maybe maybe you can combine their results into your when you apply your hypothesis to the same setting they use, maybe you can derive very interesting results.
And
why consider, so currently you do not consider the client selection, right? When you consider the client selection in non-ID, maybe you can derive more interesting results.
Thanks a lot for the suggestion. Yeah, that direction does make sense.
Thanks for the talk. It's really impressive. Thanks.
Yeah, thanks a lot for the question and the suggestion. Yeah, it's really amazing. Yeah. Okay.
There is another question from the audience. Let me unmute. Please go ahead, Shenzhen.
Hello, I have a question about the experimental result. Because based on the experimental, seems the federated MNIST is fit for the hypothesis, but the CIFAR 100 is not fit. So is this real for the federated? Is it real for the federated SGD will be better in the CIFAR 100, and so the federated average will be better in the federated MNIST and stuff? Result, does the result show that? It's still we can get different.
I see. Yeah, I think from the empirical results even on CIFAR 100, we still see fat averaging is better than fat SGD. I think the reason to explain this is that our client consensus hypothesis just say that. So under this client consensus hypothesis, fat averaging will be strictly better. But even if we do not meet this client consensus hypothesis, we can just say that fat averaging may not be strictly better, but it still can be better. Yeah. So that is the phenomenon we cannot explain. Maybe even on the CIFAR 100, the client consensus is still relatively small. This is just a random guess. Yeah, but if you look at the experimental results, such like this, the first plot corresponds to CIFAR 100. We see that fat averaging is still better than fat SGD. Yeah, but on this data set, because of the client consensus does not hold, so the method which aims to addressing which aims at addressing data heterogeneity can definitely help fat averaging. For example, scaffold will outperform fat averaging on this data set. Yeah, this is our insight from this paper. Yeah, hopefully this answers your question.
Yeah, sure. Thank you. Thank you for that.
Okay. Yeah, thanks for the question.
All right, is there any other question? Maybe wait like half a minute if anybody wants to ask. All right, so it seems that we have no other questions. So thank you, Jianyu, again for sharing your work and for your excellent talk. It was a pleasure to host you at Flow, and thank you all
Yeah,
for
thanks.
yeah, and thank you all
Yeah,
for
thanks.
coming today.